Hello everyone. This is part 2 of topic 7 for exam 1, integration involving and resulting in exponential functions. So we have two new formulas. The integral of e to the x is e to the x, and the integral of e to the u is e to the u. We saw the special case where we have the linear argument rule, and so that was worthy of memorizing, but then when we got to combinations of different classes of functions, we saw that when we have algebraics and exponentials, the exponentials dominate, and that's no matter how complicated the algebraic is. As you can see in example 4, we still had an algebraic and an exponential, and the exponential dominated. And then we saw the situation when you have exponential and trigonometric functions, and you cannot be sure which one dominates there. It all depends on the nature of the integral, as we saw in examples 5 and 6. So continuing with example 7, we have to think of other formulas if it's not going to fit one of our basic ones, and involving e, that is. And in this situation we see a fraction in number 7. And so when we have a fraction, we know the question that we ask is always, is the denominator a power? And if it's a power, we're going to go for u to the n. And if the denominator is not a power, we're going to try to fit du over u. So in number 7, since the denominator is just a function of x, it's not a power, we're going to try to fit the form for du over u. So we'll take our u to be 1 plus e to the 4x. Make sure you put yourself in the differentiation mode. Derivative of 1 is 0. Derivative of e to the 4x is e to the 4x times 4. And we tag along the differential dx. And then we modify by the 4, so we get that 1/4 du is e to the 4x times the differential dx. And keep in mind, we're trying to fit the form of du over u. We had chosen the denominator to be our u, and if we look at the leftovers in the numerator, e to the 4x combined with the differential dx, compare them to our du, and we see they match, just modified by the 1/4. So we'll replace those factors by 1/4 du, and now we can make the change of variables. So most efficiently, we'll bring out this 1/4, and upon the change of variables, we have the basic formula for the integral of du over u. And so that integrates to be the natural log of the absolute value of u, add our constant at that point, and we'll back substitute. So 1/4 natural log absolute value. Our u was the quantity 1 plus e to the 4x. Close up the absolute values, and don't forget, of course, to carry along the constant. Now, this is a case where you could remove the parentheses, because 1 plus e to the 4x, no matter what x is, will always be a positive number. So you could remove, I misspoke there, I said parentheses, I meant you could remove the absolute values, because that's never 0 or never negative. So you could replace them with parentheses. But remember, just leave them and you'll get full credit. Okay, so the difference between 7 and 8 is basically the same problem, except the denominator in number 8 is raised to a power. So again, reinforcing the fact that when you deal with integrating fractions, the question we always ask would be, is the denominator a power? And if the denominator is a power, it's going to be u to the n. If the denominator is not a power, du over u, as it was in number 7. So in number 8, it's going to be u to the n, and we should take a step to rewrite this by swinging that quantity that's in the denominator up to the numerator. So therefore we have the integral of e to the 4x times the quantity 1 plus e to the 4x raised to the negative 5th power. And the u substitution turns out is the same. That is, you're going to pick u to be 1 plus e to the 4x because we're trying to fit the form of u to the n, or in particular, in this case, u to the negative fifth. The du is calculated. That's e to the 4x times 4 again, differential dx, of course. And we modify 1/4 du is e to the 4x dx. So now the leftover factors in the integrand, the e to the 4x and the dx, they once again match our du, just modified by the 1/4. So we replace those two factors by 1/4 du, fit the basic formula, bring out the 1/4 integral, and now the basic formula is u to the n, in particular u to the negative fifth, with respect to u. So we can integrate. The 1/4 tags along, u to the negative fifth integrates to be u to the negative fourth, divided by negative 4, add our constant of integration at that point. I'm going to take 2 steps to rewrite this. I'll write it as negative 1 over 4 times 4 is 16, and I'll swing the u in the denominator now to the positive fourth, and then I'll back substitute. So negative 1 over 16 and 1 plus e to the 4x now to the positive fourth, plus our constant. Okay, and then just 2 more to go to finish off this topic. Number 9 is kind of a special one. I really actually like this problem quite a bit because you might look at it and say it's a fraction and the denominator is not a power, so du over u. But that's not going to work very well because if you consider taking u to be the denominator, its derivative is e to the 2x times 2. We have an e to the 2x in the numerator, but we have some extra terms. So this is a situation like we saw in the last lesson where it's special because the denominator is a monomial, or a single term. And we have to algebraically modify this to fit an integrable form, basically by using, as we mentioned before, the rule for combining fractions in reverse. That is, if we have a over c plus b over c, adding fractions, we need a common denominator, and then we keep the denominator c and combine the numerators, so we get a plus b over c. So this concept can be reversed when we have a monomial denominator by dividing it into each term of the numerator. And this could be extended to more than 2 terms. So that's the plan. We're going to divide everything by e to the 2x. Now, after I write the integral symbol, I'm going to need a set of parentheses because I'm about to separate this into 3 terms. And everything's going to get divided by e to the 2x. So e to the 4x gets divided by e to the 2x. And then we have minus the e to the 2x gets divided by e to the 2x. And then plus 1 gets divided by e to the 2x. Close the parentheses. And that's all with respect to x. So note that formally parentheses are necessary, because otherwise we would just be saying that the dx is being multiplied by the final term. But it's the whole integrand that needs to be in parentheses. Okay, and then we'll take a step to simplify. And e behaves just like any other base. When we divide common bases, we subtract the exponents. So this would be e to the 4x minus 2x gives us 2x. Minus, I think most people would just simply think of canceling here, and that gives us 1. But if you wanted to think of dividing common bases, subtracting the exponents, we would get e to the 2x minus 2x, which is 0, so e to the 0, which is 1. And then let's take advantage of the fact that in order to integrate 1 over e to the 2x, We don't have a formula for 1 over e to the 2x or 1 over e to the u, or we just have a formula for e to the u. So therefore, we're going to exercise our negative exponent rule and swing that quantity up to the numerator and negate the exponent. So e to the negative 2x. So I like this problem because you have to algebraically manipulate to fit an integrable form. Now notice everything is integrable, and if you want to separate it into 3 integrals, as I'm doing here, that's fine. So the integral of e to the 2x with respect to x minus the integral of 1 with respect to x, and then plus the integral of e to the negative 2x with respect to x. Or if you just jump right in there and integrate, that would have been fine as well. And the other thing I like about this problem is the fact at this point we have to use the linear argument rule. So the integral of e to the kx is 1 over k, so in this case 1/2 e to the 2x. And we have minus integrating 1 with respect to x, we get x. And then here the linear argument rule once again. So 1 over negative 2, or negative 1/2 e to the negative 2x plus the constant. Alright, so if I haven't stressed enough, I like that problem, and it may be something to consider for the exam. Okay, and then the final problem, a definite integral. And I'm going to make the definite integral such that it's identical to this with respect to the fact that it's fitting the linear argument rule. That is, this fits the form of e to the kx. You don't need a u substitution, because remember, we just used it over here in problem number 9, but just to remind you, the integral of e to the kx is 1 over k, e to the kx. And so I promise you the question I give you on the exam will be identical to this with respect to that fact that it'll fit the form for e to the kx, so you can integrate by inspection 1/3 e to the kx, 3x. And that's evaluated from 0 to the natural log of 5. Now, the way I designed this problem, the reason why I'm making the integration so easy, because I want you to simplify completely. Here, using the fundamental theorem of calculus, we would have 1/3 e to the upper limit goes in, so 3 natural log 5, and then minus 1/3 e to the lower limit goes in, so 3 times 0. But now, if we see e and the natural log hanging around together, we know that we could probably use an inverse property. And kind of separate this off to the side. The inverse property in particular that we should be thinking of here is that e to the natural log of x is equal to x. But in order to use that inverse property, the coefficient of the logarithm, that's the power on the base of e, has to be equal to 1. It's not, it's 3. So therefore, what we could do is use our algebraic log properties in reverse and express this as 1/3 e to the natural log of 5 raised to the 3rd power. And then this would be 1/3 e to the 3 times 0 is 0. And then continuing, we'd have 1/3 e to the natural log of 5 cubed is 125, minus 1/3, and then e to the 0 we should know is 1. But then e to the natural log of 125 is 125 by our inverse property. And so we get 125 over 3 minus 1/3, which gives us 124 over 3, and that can't be reduced. So that would be our final answer. Okay, so some important problems, and guaranteed you'll see many similar questions on quizzes and exams.